Now, the quantum diffusion has been around for a very long time. Some of you might have heard of the work of that got the one of the most celebrated work of quantum dynamics is the Phil Anderson's metal insulator transition. That means what one finds that certain amount of disorder a metal undergoes insulated. That's there are several mechanisms of that. One of them is the Anderson localization. So, title of his talk was absence of quantum diffusion because of disorder, and disorder means in quantum systems, in classical systems if you consider disorder, we essentially like a liquid is an ideal example of disordered system, crystal is an example of an ordered system. And so, when we in classical system we talk of disorder, we talk of mostly what his thesis called the topological disorder. Topological disorder means I give you location of one atom or molecule, you won't be able to tell with certainty location of another atom or molecule. So, you have to talk in terms of probability and enters the description like radial distribution function, structure factor, those kind of things. And you have read in your undergraduate some of the ideas that Boltzmann, Ludwig Boltzmann introduced long time ago, and then also then Willard Gibbs and those people. These are all classical systems, and in classical systems disorder is, as I told you, is largely a topological disorder. In quantum systems however, your concept of position, momentum, like in a classical system you take a velocity distribution, momentum distribution, that is the Maxwell distribution. But in quantum systems these things are all go over to the wave function and the energy levels. Now disorder essentially means comes in the form of the disorder in the energy levels, okay, and the disorder in the coupling between different such energy levels. And and with that the disorder can be static, that means if I have two level systems, and another very important thing that will come in a second, then the coupling between these two, let me, why am I using my AI, let me use, I have a board. So now see when we talk of atoms or molecules, those who photodynamics they think of much of the time a one atomic or molecular system. The systems that I will consider today will have the extended system, that means I will have this kind of they need not be regularly placed, but let me place them for some reasons that I will use later. So the kind of things that I am going to talk today is the extended quantum systems. Extended quantum systems are the ones that physicists always talk about. Chemists usually avoid the extended quantum systems, except chemists were made to think about it in two cases. One of the case is the conjugated polymer, which are called organic semiconductor, which are now used in many places, solar cells and many other things, where your energy has to be transferred from one place to another place. And we physical chemists talked a lot about it, that how that energy transfer takes place, and I will talk a little bit about that. But for last 10 years or so, what happened and what many physical chemists and physicists and biologists started working on one problem, which is photosynthesis. In photosynthesis is the fundamental life on earth, which gives rise to this way of taking these things, and this goes on to ATP, and which is the energy molecule. But all this happens with the absorption of light, and then light goes around in these chlorophyll systems and goes to the, so light is absorbed by these chlorophylls, what we call antennas, then they go over to reaction center where water is then broken into oxygen, and then an electron is stripped off, and this essential process goes on to sugar and that then ATP and other things. But I am not going to go into all the details, but basic thing that I am interested today, and that has, I was telling you, remarkable similarity to another problem that we have been working, we means physical chemists and physicists have been working on, that how the energy gets shuffled between them. How does the energy, if it is absorbed here, how does it go there? Now one of the way it can go, that energy hops from here to here like that. It has to go to the reaction center where the initial live process starts. Now it can go hopping, which is a random walk. I will talk a little bit of random walk and hopping, or it can go in a very interesting way, that which is possible only in quantum systems. There is no classical counterpart. That when light, when it is absorbed, immediately after, but at the time of excitation, energy is sprayed all around. That is quantum mechanics. That means your wave function is extended. You cannot say that energy is localized on one. These, you can consider each of them as two-level systems, just like my two-level system, but these two-level systems are coupled, and they are coupled, and this is a very important thing that comes in this system, but not in atoms and molecule, is an exchange integral, we call it. This is purely language that we have in a Hubbard model or those kind of models in physics. Okay. Because of this, of what we call, so this is not an kind of diagonal coupling that we do in chemistry, where there are many energy levels and you are coupled between them. Those complexity is there, but at this time we don't need to talk of that complexity because we can absorb it. What we are talking is that these are different spatially, spatially, spatially different locations. However, because of this coupling J, now when you try to find a wave function and diagonalize it, you find out that the wave functions that you get, there are three level, I diagonalize, I get three wave functions. You find all the wave functions called elements of each of the side. This is called side representation, but in the real world what happens is the excitonic wave function of this is zeroth order Hamiltonian, and after you put the Hamiltonian, so the real wave function, I will not be too much of quantum, but there is nothing. So this is the coupling. So in our description, this thing is the side representation. However, when you go to the real wave function of the Hamiltonian, everything gets mixed, and that description will give rise to what is called coherence. It will become a little bit more clear with time as I go on. What really created huge amount of excitement, and one thing that a student should certainly remember, that this is not because I am working on this problem, we just have done not too much on that, but this is a wonderful problem. You should always work on very important problems. You know, a scientist is known by the problem he is working on, and this is a major, very major problem, the photosynthesis, both experimentally and one of my colleagues who worked on this told me every decade they have given Nobel Prize to photosynthesis, somebody doing photosynthesis or similar things. Solar cell now has taken over the same thing. All the excitement started essentially with this paper in 2007, as I said, about 10 years, a little bit more now, when they discovered, and this is no earlier work that was ignored, that if you can look at the anisotropy decay, that means you use the polarized light, excite, and you look at it with a different polarization, you would find that that undergoes an oscillation. This is not common in atomic or molecular systems that much, and over a rather extended period, few picosecond. Then people did higher order laser spectroscopy experiments, and they again found these excitations. And then when go back and people do this, then what one can deconvolute and find that energy actually going back and forth between them. That means these suddenly you see, if you say energy is red and lack of energy is blue, you will find the movies people have made by transferring these results into wave function, and from wave function into this population, site population, you will find that energy is spread and that energy is going back and forth between them and surviving for quite some time before going to reaction center. I am saying this is not an easy problem, but some things I hope will be able to explain. So, why should one be interested in quantum coherence? As I said, it is inherently quantum phenomena. This is no counterpart in classical mechanics or classical statistical mechanics. The people are using this in quantum computing. You might have heard the name quantum entanglement. All these things are essentially manifestation of quantum coherence, and the basic idea is that it provides a much faster, the reason one is in quantum computing, is a much faster transmission of information that you know want in quantum mechanics in a computer. And then, as I already told, the another major people have been working for last about 20-30 years is semiconductor. Much of the formulation, language, many of the things are common, except that quantum coherence is far more in photosynthesis, and the reason so it became, some of the papers in this field are 4,000-5,000 times cited, people talking of Nobel Prize, partly because it has gone into quantum computing and quantum entanglement. Okay, this slide I didn't have yesterday, and coming back to a very where quantum and one dimension, there is intriguing similarity between classical and quantum. So, this is the example I talked about, that islands formed by traps. These are famous two mathematicians, Stein and Newman, Courant Institute, and they are saying that okay, you start here, can you go to the sea, and if you have only narrow channels, then they showed that if you can doing that in 1D like that, then if there is a huge disorder, that means you just make one very weak, you can really slow down water's migration. Why it is so? The one dimension is very important. So, diffusion, these two people, gentlemen said, diffusion in one dimension is pathological. Now, if any of you have done one dimensional systems in conductivity in one dimension even infinitesimal disorder localizes conductivity in 1D quantum systems. 1D, and I will tell you, I told little bit 2 days ago, the pathology of 1D, because there is no escape. In 2D, for example, if this is one dimension, and in classical systems, random rugged landscape means there are maxima and minima, barrier and minima that I talked last time, and if I try to execute a random walk, which is diffusion, and if I find a large barrier, and if ruggedness has a distribution, I will ultimately have a large barrier, then I reflect back and I trace the same path back, I again get a large barrier, I again trace back, and that makes it pathological. But in 2D, why there is no problem? And the same in quantum systems, 1D is a slight disorder localizes, not the same as 2D, because 2D when I am going back, I have infinite number of possibilities, you know, where I can escape the traps. These are really very interesting things, but I am trying to make it as simple as possible. So, this I talked yesterday that protein folding, this Zwanzig did this thing. The reason I am talking today, I need little bit of one of the things I require, that is he showed that if there is a ruggedness, that means if there is up and down minima and maxima is distributed according to a say Gaussian distribution with epsilon, then this is the beautiful very famous expression he derived, that it gets quenched, not in Arrhenius way, but what we call super Arrhenius way. Now, one thing is very important in classical or quantum system is the relation between diffusion and entropy. This is something everybody should know, that in condensed matter science we use, it is amazing because diffusion is a transport property, right? It is a time dependent relaxation, and entropy is entropy is a thermodynamic property. So, you take out the ideal part, sometime you take minus, sometime plus, depending on what you are doing here, you can write it around. When you take out the ideal part of the entropy from entropy, we call it excess entropy. One finds the diffusion is connected to that, and that's found in very large number of systems, very peculiar relationship between a transport property, a dynamical quantity, which is diffusion. How far mass is moving, that's diffusion. And what is entropy? Entropy is a thermodynamic property, right? That we know so well. So, in a system, one finds, and this is one, but there are many other relations, or actually one more relation, not many other, just two relations. Both find that diffusion and entropy are very intimately connected, and this works extremely well. In India, a lot of work went into that, because there is a lady scientist who was our favorite, who died. It was a Charushila Chakraborty. She did a lot of work on this. Got Bhatnagar, but she died. We lost her to cancer. So this peculiar relation drew a lot of attention worldwide. See, one of the reasons of this lecture series or distinguished professor, that we expose you to new things, different things. And this is one of the really spectacular thing that is happening in condensed matter physics and chemistry and protein and everywhere, is this kind of relation we use. Diffusion, a transport property, a dynamical quantity connected to a thermodynamic quantity, that is the, okay. Now I will show you a very simple derivation of this quantity. There was no derivation before our derivation. Here this is the first, that you can believe me, first time we gave a derivation in a very, very simple way. What I drew last time, that I have a system like that. Like a rugged landscape. So these are my minima, and these are the maxima. Okay, this is kind of a transition state. So now, if I give you a distribution of the minima and maxima, then this is the energy, and these are my sites. All are my sites. Then I can relation free energy is get by the logarithmic of something called partition function. This partition function is this quantity, which can just be calculated exactly in these kind of cases. When you get the free energy from partition function, trivial, that means you can do the back of the envelope calculation, all of you can do it. Then you get entropy, remember entropy is temperature derivative of free energy. Then you get this quantity, this is exactly the ideal gas counterpart of the entropy, which is ideal part. So this part comes out, this is the extra part. So you define Sx, and now you use Zwanzig's expression, then you get this relation, scaling, because this is Zwanzig's expression is square by kBt. I showed that the entropy is E square by kBt. So D is, understand, na? Look at it again. So I calculated entropy. Zwanzig tells me this is the quantity. We have done a far better, completely, not even using Zwanzig we have derived, but I am not going to talk about that. It's far more sophisticated. So now if I use Sx, which is this quantity, I put Sx here, then I get exactly this thing, which is called Rosenfeld scaling. It's a very famous thing now. It is using in glass, using in proteins, using in bio, because it is so tempting. It is so tempting because if you have entropy and you have diffusion, or you have diffusion, you can have entropy. It is a parameter. In our case, that's equal to 2. And when you fit it in liquid state, actually you find it very close to 2, and this you get close to 1, which is. Huh? No, this is, I derived it for 1D. Now this is mean field calculation, this is true for any D. But because this dimension doesn't come in here, I can have this kind of distribution, I can do that. More important is that this scaling people have found varied for many liquids, binary mixtures. Charu did both for binary mixture, water, it works very well for water. This is an amazingly simple thing, but it is a tremendous amount of insight that you get. Okay. Now I will go back to again a little bit of quantum diffusion. I will go back and forth between classical and quantum mechanics, because otherwise it gets very complicated. So this is the many people's hero, nobody understands quantum mechanics, and if he says that, the only thing we know about quantum mechanics, from Feynman, understanding, it's amazing to read his books. I have been reading some of his papers and books, Hibbs and I remember before when I got offer from Brown to do PhD, first thing I did, I went and bought those 3 books of Feynman, red books, big lectures in physics, 10 rupees each, and College Street, and I studied them. Particularly quantum was the really best part of this book. Anyone with quantum mechanics? Okay, now it's a great book. You should read it. What is life? All of you should. I think you get it free on the internet now. So if a man never contacts himself, it isn't maybe that he virtually never says anything at all. Now again go back to diffusion and localization. All his classical diffusion theory started with Einstein, 1905. He showed that it is essentially random walk, and you get always diffusion in classical systems. Come Anderson localization, he said no, it is not that. Classical systems, if you have a disorder, for example, if I have a site energy disorder or disorder in the coupling between them, here I taking only of the site energy, that means there are 2 level systems. These 2 level systems that I have drawn here, but they do 2 level systems, I make them like that. Okay, that means this gap is fluctuating, and that given by square distribution W, then you can show that it is always localized in 1D and 2D and 3D. It localizes when these becomes bigger than that. Why? That is what we will try to understand, that the uniformly distributed random site energies, and that and title of his paper was, as I told, absence of diffusion in certain quantum systems. Okay, now I will give you one example how quantum and classical are different in a trivial example. All of physical chemistry know this. This is my ground state, I have a 3 level system here, okay, I am exciting it there. And I write an Hamiltonian, which is the external field is this excitation, and there is a coupling between them. It can be coupling between this and this, this and this, and this and this. That means I have a V 2 3 1 2 and 1 3, and then I can have these diagonal things which are, so coupling is fluctuating. I don't have J, I just have a time dependent fluctuating around 0, it is fluctuating. Now in this very simple system we know how to calculate the rate. I am not going to go into that, but I will calculate the rate like this. I can calculate. Now I do a simple experiment. I go and solve the time dependent Schrodinger equation, because this is a Hamiltonian, it has a time dependence. I can go and solve time dependent Schrodinger equation, right? d psi dt equal to I by h bar h psi, right? Then I can find out how it is relaxing. So in classical mechanics, if it goes from here to here, here to there, this channel, if I keep it on and off, does not matter, okay. But in quantum mechanics, whether you turn it on and off makes a huge difference. Why? That because they are in this path of relaxation and this path of relaxation interfere with each other. And this is called quantum interference. This you have heard a lot in cases. Now I again go, this is first just a preparation to you. Now we are, I am telling you that we have worked a lot on that, on the freight and conjugated polymer, MEH, PPV, PPV, all these kind of things that we have done. And this is connected to also the photosynthesis. Again, I told in the beginning, let me again tell what is the difference between coherent and incoherent, why so much interest is there. If it is a coherent, the energy is spread all over and you have a sink there, then you can take it off. It is not that easy, but that is the whole interest, the why photosynthesis is so efficient. We have never been able to do anything above 25%, right? Though perovskite now and then comes this efficiency 90%, then but this 90% for femtosecond, after 1 or 5 minutes it goes back to 20%, right? But nature is 100% efficiency and we are all very grateful for that. So the idea was that in photosynthesis this energy transfer is coherent. That was so much excitement. So everybody is involved. So everybody knows there is an excitation. Okay. But classical would be it goes there, comes back, go like this kind of nest, it will happen, and this is slow. It's not necessarily is fast. There are many other complexity that comes in, but we'll talk about that. So one thing is a wave function representation. So wave-like transport, superposition, as you know in quantum mechanics, as I said, the excitonic representation, but here we have a incoherent hopping and particle or side-based representation. Now I will do few of the things which is slightly difficult, but I will come back and forth, and if it gets too difficult, I have a freight talk, I will go over to freight talk, and that anyway you guys should know that freight thing. Okay. So I am now going to talk of these things. My student who has did these things, he just exactly the opposite that I tell him to do. So you see red should be excited blue, so he just opposite he has done. To me always red is excited. He said no sir, red is the low energy state. So red is the, now what I have been telling you before, I can have a Hamiltonian which is like that, I can have, I diagonalize it, I can have a representation where J is 0, off diagonal coupling is 0, that I will get the side representation, but when the coupling I can diagonalize, I can get the two energy levels and wave functions. So when the coupling J is very small or gap is large, I get the localization. Then my side based representation and hopping works out okay. But what happened when this J is large, then you just have one system. Your whole energy and your wave function is delocalized. What is happening in between? And more importantly, what Anderson didn't ask, we are going to ask, what happened if there is a dynamic disorder? So let me again recapitulate what I am going to talk. We have published several papers on this in last year and this year. So this is my system. I can write easily Hamiltonian of that, and this is my coupling J. Okay, J. Now dynamic disorder means this is fluctuating, site energy is fluctuating, J is fluctuating, off diagonal fluctuating. So I now write a coupling of diagonal coupling which is time dependent, that I add to J, and I do just like Anderson did a diagonal fluctuation, but Anderson had it just static, I now want it to fluctuate. So this thing is fluctuating like that. Can I just finish this one? So this is fluctuating. Now, so that makes a tremendous difference. Quite. What Phil Anderson said, okay, he has this thing, he didn't have this thing, but he had this thing, but he had this just randomly distributed, and he showed on beyond certain randomness, electrons don't know, electrons get localized over a domain, and that's the insulator, metal to insulator transition. However, consider you have fluctuating. So let's see, I have a situation like that. Then what Phil Anderson will say, that wave function will get localized here, wave function will get localized here. However, if these are dynamic disorder, if it so happens, I am not saying this is applicable to 166, no sorry, Phil Anderson 6, but many other cases that we will be talking about. However, if these fluctuates now, when this gap comes to this gap, gate opens. Okay, so this is called dynamical disorder. That means disorder can promote transport of energy. Yes, tell me. Right. J is not fluctuating, J is rock solid constant. J is rock solid constant everywhere in the whole of physics, whether any model you can take up, Hubbard model, Ising model, everywhere, J is constant. J is constant. Then we are saying in addition to J, there are two other quantities. One is the fluctuation of the energy gap, that I am calling Vd, and there is a fluctuation in even this, that is added to J. If I take the average of this, I get J. If I take the average of the, I get 0, because this by definition a fluctuation is something, the way I define it, average is 0.
So I understand. What you trying to say is that essentially some factor between the energy gap is added or subtracted.
Right.
That is leading to the factor.
Or you know, that is one thing, but other big source is the diagonal disorder. Anderson considered only side disorder. You know, his J was constant. He considered a static disorder here. He did not have this term at all. Okay. Oh, you cannot see that. Yeah. So no, I think I can. It is I can use anytime. I am saying again like that. Huh? So what I am saying, this J, that's constant. But in addition to J, I have one more, let me call it like this, that is VOD, and there is something gap fluctuating that I call VD. Is that clear now? No, I don't need. I don't need, but the stories are different with the two fluctuations, and they are very rich field. You know, I'm not going to do a good job on this beautiful field and this huge field. Huh? Yeah, very, let's say conjugated polymer, or let's say photosynthesis system. There are a lot of dynamics going on, right? Photosynthesis, I give you the answer, you know, though it took me a long time to realize. The reason we see coherence in photosynthesis system is the off-diagonal coupling J is larger than KBT, period. And that people didn't tell, but we started doing, we realized that. Now, so let us see conjugated polymer. So the MEHPPB, or their side chains, they are all fluctuating, they are all moving around. So your J term is moving with that, but these things are all I can consider fluctuations. They are anharmonicity. So I have an average value of J, but I have fluctuations in J. Similarly, my site energy, it is thermal bath is there, phonons are there. Physicists don't talk of these two things, but when a physical chemist starts working, that's the first thing physical chemist starts thinking about, because that's where our rate constant also comes, you know. It goes back to a great extent to Rudy Marcus and then great work of David Oxtovey and other people. Okay, now getting little bit dirty. Now I write my Hamiltonian as I have done: system, bath, then interaction between bath and the system. My system, look at that now. It has it is in side representation. This is sum over k. So I multiply by k on the left hand side and right hand side, I get this E naught. So that energy gap is constant. That energy gap here, though I have written it fluctuating, it's constant. This is the coupling. JKL is very much like Ising model or Hubbard model. This off diagonal k not equal to L, okay, but I'll make that J is in constant. So I'll remove, just I do in Ising model, remove the subscript k and L, I bring it in front J, okay. Now, you know, when a theoretician starts talking of Hamiltonian and this kind of coupling, he just enjoys it, you know, but the rest of the audience don't enjoy it, you know. So to us, Ising model, Hubbard Hamiltonian is so that you know, we feel very innately happy as you have given me a good glass of wine or something, or even orange juice. But I think the rest of the people are just, it's a torture. So now, however, I now go to what is called the interaction representation. I remove that part, but this becomes then time dependent. So now these sides are having certain time dependent fluctuation. That, as I said in my model, I divide into two parts. One is the diagonal. Diagonal means same side, this VT, and there is an off diagonal, which is VOD. By the way, the next lecture will not have that many equations. Okay. So now there was a great scientist in our field called Rigo Kubo, who did this fluctuation dissipation theorem and many things that we know comes from Kubo. This is not a great picture actually, but that's all I could get. Kubo said, okay, let me find a way to describe, I know how to describe in terms of Liouville equation, but I have to now go Liouville equation, which is a very complicated equation, go beyond it, and then called stochastic Liouville equation. He formulated that in a, so this is my Liouville equation, this is density matrix, Liouville equation, and then this V is the fluctuation, this is a master equation. he combined these two by beautiful way. He said, okay, let me define a probability P V rho t, which is in terms of the delta function. That means probability that along the trajectory fluctuation V has value V, then density matrix of the system along its trajectory has value rho. There is a beautiful book by Haken, Synergetics, Introduction to Synergetics. He popularized this kind of a description. Now, what he did was different from other people. He was absolute genius, should have got the Nobel Prize. Now, he said, okay, I now define a reduced density matrix by averaging, this is the general probability distribution, averaging over the density matrix of the system, and then I will have some properties of the rho left in the Hamiltonian, but otherwise this population of the system is averaged over, but what I am left is the bath. There is a very unique way of doing. It is not the stochastic level equation people physicists use like Redfield equation, but this is a far more sophisticated equation because you have a bath degrees of freedom explicitly left, okay. So now what important thing is that this, the one that is remaining here, the bath part, you expand in the eigenstates of the bath. Bath can be a Gaussian bath or Poisson bath. If you expand that, then you get a very complex set of equations which are here. I am not going to describe them, but then you can, and it becomes more and more complicated. One beautiful thing, however, if you look into the equation, what you will find is that there are two kinds of terms that come in. One is the ground state of the bath and the excited state of the bath. This is the quantity you want. This is the excited equilibrium state of the bath state. But here, however, this is the excited bath state. So in this rather very complex description, both of them are coupled. And when you can solve that, you get a beautiful set of equations. That equation is the mean square, forget about the upper one, the mean square displacement. In case of diagonal fluctuations, you get this term where J square is here, the constant of diagonal coupling is here, but that is traced by the magnitude of diagonal coupling and the time scale of diagonal, B is the time scale of coupling, and then J again is the constant of diagonal coupling. That traced, this is a beautiful term. If I do not have any coupling, look at this term. If I then this is the mean square displacement, how far the excitation is going as a function of time. If I do not have the fluctuations, then you see it goes as t square. That is called coherent motion. That means it goes ballistically. However, fluctuations make this ballistic motion, short-lived. Then it becomes diffusive. And then, however, these things now get scaled by these fluctuations, and this is a complex function, but analytical. But we could not do it in when bath is correlated, non-Markovian limit. I don't need to go into that, but the basic idea to tell that these fluctuations really give rise to completely different behavior in quantum systems, and these are published. You can see that. Now I show you how the fluctuations. This is a beautiful set of equations, but I get tired always describing them. Right. Right. Okay. Let me write down. Let me write it down. Let me define first the. And also part of the reason I don't define most of the things. This is the correlation function. Okay. So things are fluctuating, but they are correlated in time. They are also correlated in space, but I am not going to talk about that here. It gets too far too complex. Now, there are two kinds of fluctuations. One fluctuation is this, another fluctuation is this. Okay. Full equation with both the two fluctuations on, nobody in the world has been able to solve. These are my equations. I have not been able to solve, and it's just horrendous to try to solve it. Even this is very bad. So what I have done, I have solved it such that after writing those equations which are given here in the full glory, I made the approximation that I said, for example, let us take this one. I put off diagonal fluctuation to 0. J is there. because that's not causing me too much problem. But it is very difficult to take both of them. So I put this. Then I get, this is the expression for the diffusion. These are all as a series of two level systems regularly placed.
Right, but when I say the J, I am neglecting.
No, J I am not neglecting.
Not neglecting
J is constant.
of that.
J is the main driver.
Yes, yes,
J is kept constant.
constant.
But I have now, see, okay, there are two issues here and two beautiful issues. One is the coherent motion or ballistic motion. So I have only J, I have no fluctuations, then it is purely coherent or ballistic motion. That is T square, okay, no dissipation, nothing, no retardation, it goes. Now I have fluctuations and they slow it down, okay. Now they slow it down two ways. It can slow it down by this, because why? Because it's trying to go, energy comes here or in a region here, it finds this guy has much smaller energy. So then he has to wait for it. What does it make? That makes your migration incoherent. So I go from coherent, it forgets its memory. Incoherent is exactly what it means in English language. You forget the memory. And forgetting memory means we are going to random walk. One of the things Einstein taught us is that you get diffusion because you have conservation of mass. Diffusion is nothing but a statement of the conservation of mass, but at the same time without memory. So mass has to go from one to place but without memory, that is why diffusion. So I get in limits, long time limit, large Vd or small Bd, Bd is the fluctuation. How it is fluctuating is rate of that fluctuation is B. So B is large means it's fluctuating very fast. Yes. T equal to 0, it's 0. So these are okay. T equal to 0, there is no displacement. Mean square displacement. What bothers you last term? last term bothers you. It should work out okay. Okay, let's T going to 0. No. T going to 0, I'll make T going to 0. This cancels this.
1 minus x.
Yeah. No, yeah, T going to 0, don't have to expand, just put it equal to 1. This gets cancelled, this one exactly. Now some examples, real life. So we solve this 7 side, 9 side, in some case much larger system. The full thing we could do 11 with diagonal after everything, we could do up to 11. And in the absence of some cases we could do up to much larger, but I'll come to that. So in the non-Markovian thing, when there is a memory and this BOD is small, the B is small, that means it is slowly fluctuating, and the coupling and J and V are comparable, then you get lot of oscillations. And these oscillations, at anybody in photochemistry and photophysics knows, are signatures, same thing that Graham-Fleming observed, the population going back and forth. That is the coherence, okay. However, in a Markovian limit, when I make B large, B10, okay, large, and V I make J is the one which supports coherence, I make it small, I go to fully incoherent limit. Many different things. These are hard calculations, you know. Okay, now there are some very interesting thing comes in. Let me go look at the mean square displacement. How does it behave? Does it always being coherent become fast? No, many times coherent. The problem with coherence is that it goes there, but then it is all extended, then it can come back again. Okay, so you need a mix of coherence and incoherence to get fast diffusion. That is also the conclusion by Bob Silby and Jiangsu Kao and other people. They did it before us, their feature article, heavily cited feature article. Okay, but this is the result that we got. They used a very different technique than our technique, and we didn't fully know of the result. But our results, they didn't have the kind of numerical and the kind of detail that we have. But then on the other hand, they were more married to real experiment, we were more married to our stochastic level equation based model, but that already has very lot of features in it. But you can see that many times it would go here, for example, diffusion. Diffusion would increase by moving very fast. but then it comes back. So your this is the Markovian limit, much less. Look at that, it just get killed. So being coherent doesn't help. Are we right? Then we say, but then we took a system where you kill the coherence, but still there is diffusion. Okay. Then we have a very large system. We had to go to a 51, and we found there is still quantum diffusion. Actually, this is the limit many people study in stochastics. We have the mean square this diffusion, time derivative of mean square displacement, and you get asymptotically. By the time we go to 51 lattice sites, we do get the expected result. This dash line here is the result, dash line is this result, okay, and in the limit of j small or j going to 0, and this is the exact numerical solution of the quantum stochastic level equation. Okay, this is, I do not want to bore you with that. The oscillatory population time correlation function in non-Markovian limit, and what term is a Markovian limit. So all these things can be done. So then one of the way to study quantum coherence is through line shape, and that would be very, I will come a little bit of that, but if I may, I can go to the one thing where I will talk a little, that will be, so this is, many of you know, and those who are doing experimentalists do a lot, which is FRET, fluorescence resonance energy transfer. This is something we did a lot of work at one time, a lot of work, including many feature article papers, PRL, or with them in Nature, 2 feature articles actually. It is a lot of fun to study how energy goes back and forth, but this is incoherent. So we just want to see how energy can go from one place to another place you attach a dye to DNA, and then you can make it there and can see how energy goes from donor to acceptor. You can increase the distance and you can break the coherence and all this kind of stuff. The famous experiments of Bill Eaton. So fluorescence resonant is a conjugated polymer, and dye molecules is a huge thing, metal nanoparticles, which has been very widely used as a metal, as a fluorophore or absorbance, because the 2 dye molecules fluorescence resonance energy transfer is only about 20, 30, 40 angstrom, but with a dye you can go up to few hundred angstrom energy transfer. Now one very important question, and that is the only thing that I will discuss here today. This again come back to chlorophyll and photosynthesis. So the one that those of you who know little bit Foster energy transfer, you know that if I have a donor acceptor system, distance r, and an acceptor system, and I want to know the transfer, Foster energy transfer, then that is k naught is actually non-radiative radiative rate kd r naught by r to the power 6. How many of you know this expression, Foster? A lot of people should know, because they are very important, like just the electron transfer. Or, no, 5 guys raise their hand. What are you teaching? 6. Arindam raised his hand. Okay. Okay. But however, what is important about this thing, the Foster energy transfer, is that we call it spectroscopic ruler, because it is a very sharp separation dependence. However, that thing depends on a very big assumption, is that donor and acceptor are both point dipole. So they are dipole actually induced dipole interaction, that becomes 1 over r6, 1 over r cube square, but it is a point dipole. Now look at this, if energy transfer in photosynthesis is taking place in retina, taking place from carotenoid to bacterochlorophyll, look at that, this guy is 25 angstrom, this is and they are separated by about 15 angstrom. So point dipole approximation is garbage, right? Because it is so extended dipole, this is dipolar density we are seeing in excited state, so extended dipole, where is the point dipole? So does it work at all? I worked it out, I knew long time ago that Foster is wrong, because I did some work on dipolar liquids where I knew point dipole just doesn't work at all. Okay, and there are many other systems, Forster energy freight, in folding up chymotrypsin and all these things people have done by freight. Very popular technique, you know, even in our country also many people are working on freight. So then we did a calculation of that, very interesting calculation, and to really do a full quantum calculation, I just show you the result. So this is a Forster again. This is a derivation of Forster through Fermi-Golden rule. Those of you remember Fermi-Golden rule, it gives a rate in terms of wave functions, donor and acceptor. This dipole-dipole coupling, because that's what it takes energy. This is a ladder. This is a ladder coupling between the two. These are sites in donor and acceptor. Okay. What Forster did, made this separation, and point dipole approximation removes the length scale from the system. It's a beautiful language here, that it removed the length scale of the charge distribution, and it's a really very nice concept, and that allows Forster to write its beautiful expression. Okay. So it's essential that you make a point dipole approximation, because when you play that game, it's a beautiful derivation actually. You know, everybody think he should have got a Nobel Prize. He was a remarkable man. They invited me 100th centenary in Göttingen, and I visited the lab and everything. I gave a plenary lecture which was very nice, because they loved this work. So now I did the excitation energy transfer between, really with the help of Peter Oski, these energies from TPP going to these different orientations, and with Forster, this is Forster. We could do exactly everything, including Forster, we could do exactly, because we had everything. And this is what happens when it comes closer together, even at 2 nanometer, 3 nanometer away, is a 2.5 nanometer, the marked deviation from Forster, and that plays a very important role in photosynthesis, in the energy transfer that I talked to you about. People used Forster before that. So first inkling that coherence is important came in the breakdown of Forster. Then we didn't know what exactly was happening, but we knew point dipole approximation is wrong. Okay. This little paper is a heavily cited paper of some 300-400 times. So results of explicit quantum calculation, size of the donor acceptor larger than or comparable distance between them is very important. Transfer rate becomes, say, 1 over r to the power minus 4, it goes to then r to the power minus 2, it also goes, but weaker at smaller. Crossover happens in this system 4 nanometer. But however, when you go out to 10 nanometer separation in this TPP and the PF system, polymer system, there is a quantitative agreement to exactly agree with Forster as here. Otherwise, breakdown of Forster. There are very interesting things. Significant amount of energy transfer takes place in optically dark states, which are not shown up in absorption of fluorescence spectrum. So optically dark state carries a lot of energy, which completely mixed. But we got it. I was very excited, but before that, Scholz and Fleming had it. We had the paper result in 2001 or 2000 and published only in 2004. That happened when you do work and you are in different places. So they are very nice. So thank you for your, I think, then dye and nanoparticles and some very, very nice things can be done. But that will go on forever. And beautiful, really, I told you, these are the favorite of theoreticians. And this line shape and Markovian, non-Markovian is a wonderful stuff there. I am not going to talk of that. So the work was started, then just pathological thing was started by Shoikat and Seki, and we got stuck 2-3 places where my son was then staying at home. Both the two problems, he helped us out, and quantum coherence, all these things have done by student Rajesh, who stubbornly refused to make good slides, and thank you for your attention.